Hi, my name is Hannah Jane Pritchett, current U of A GIST Master's student and UA GIST podcast host, along with Chris Lukenbiel. Welcome to the University of Arizona GIST podcast. Today, we will be chatting with David Nelson, a data manager, GIS specialist, and planetary geologist. Let's get started.
Hello, my name is Chris Lukenbiel. I'm the director of the UA GIST programs here at the University of Arizona. And today on our podcast, I'm delighted that we have David Nelson, a geologist, a planetary geologist, data manager, and system administrator and GIS analyst for the Ronald Greeley Center of Planetary Science at Arizona State University. David Nelson and I go way back in the GIS world together, where he helped significantly with the foundation and development of the MAS GIS program at Arizona State University. And also joining me today is Hannah Jane Pritchett, my delightful co-host that keeps everything together on a daily basis for us. Hi, Hannah Jane, how are you doing?
Hi, I'm great. Thank you so much for joining us, David. We're so excited to have you. Chris, you want to take it away?
So, David, would you mind telling us a little bit about what is the Ronald Greeley Center for Planetary Studies and how did you get started with them?
Sure. So first of all, good morning. Thanks for being here and thanks for inviting me. So the basic idea, the Ronald Greeley Center for Planetary Studies has a long history. It starts with the namesake, Dr. Ronald Greeley. He originally worked on the Apollo missions as a mission scientist, helping the astronauts with the learning geology in the field, as all but one of the astronauts were pilots. So they needed some help learning to look for what types of rocks on the surface of the moon when they were there. He eventually came to ASU in 1977 as a faculty, and then he established the Space Photography Lab in 1980. This was a photographic archive back in the 80s and 90s. So if you were a planetary scientist at the time, planetary data were not widely available. It was all photographs, maps, paper products. And if you were working somewhere that didn't have those resources, you would come to ASU, you'd book a hotel, you'd stay there for weeks, and do all your research in the center while you were there. And then you'd go back and write up your reports and so on. Well, we are now in the 21st century, so we are making this more of a digital archive. We're becoming a data facilitation type of center as opposed to paper products. Ronald Greeley actually passed away in 2011, and so the center was renamed from the Space Photo Lab, SPL, and was renamed after him, the Ronald Greeley Center for Planetary Studies. And so one of his postdocs, Dr. David Williams, actually took on the position as director, and he is continuing that role to today. And he has actually been on a number of active missions, including the Mars Express, the Dawn mission that went to Ceres and Vesta, and will also be on Psyche. So he's involved directly in planetary missions. And then our center has gone from a library where we do research with the paper products, and now we turn that into a GIS lab where we can take mission data and work on it in a GIS fashion. So that's kind of where, the long history of where we've been and where we are now. And we're still kind of in development, going from all paper to GIS is problematic. And the other thing too is that GIS was not widely available for planetary. The data are just different from Earth studies, Earth data. And so we had to come up with a way to work with planetary data in a GIS system that was designed for Earth data. So we can talk a little bit more about that. As far as myself, how I got involved with them, I actually came to ASU as a graduate student, a master's. My undergraduate was in geography at San Diego State, a place that I think Chris is familiar with. And when I went to industry for a while, I actually worked at Camp Pendleton Marine Base in California. And there I was in charge of the GIS for their environmental systems. And that was just a short stint because in 1993, I found out that we were going back to Mars. We hadn't done much in the way of planetary for a very long time, and I decided this was my opportunity to go back to school and be part of active missions. And so I actually became a master's student under Dr. Ronald Greeley, and worked on some mapping projects, got my master's degree there, and then continued on a number of more years as a staff person. So that was my introduction to the Space Photo Lab as I worked on my master's project. And again, because of the nature of the data, my mapping project was paper maps, photographs, Mylar, pens and paper. And that was the last big project that I did that was non-GIS. And so that was cartography. That was planetary cartography from all the way in the early days to the late 90s. And then I stayed on with Ron for 5 more years and kind of pushing the GIS. That was developing at the time for planetary. People were starting to bring data sets into ArcGIS and trying to work with data on a global sense that had the different datum. You know, Mars has a different shape, Moon has a different shape from the Earth. And so that was challenging. And so I have to give credit to the USGS and Flagstaff. A number of people there were instrumental working directly with Esri in order to get planetary data in a usable format that could work with ARC. So you would have a Mars data set that's been reprojected. You can drop it directly into an ArcMap project, and it will actually recognize where it is. You can work with it spatially, make measurements, draw right on it, just like you would with Earth data. And so from the early 2000s, ARC has been a way to work with planetary data for the last 15 or so years. After I worked with Ron up until about 2003, then I went back to the geography program at ASU to work on GIS there, and that's where I met Chris, and that was probably around 2005, 2006, that time frame. That's about when you came to ASU, right? Yeah. And so I worked on a degree there. The original idea was to get a doctorate. I didn't quite finish. I got ABD, but I did get my master's degree there. And one of the things that kind of caught my attention when I was in the program was there was a lunar mission that went to the moon in 2009, and that was called the Lunar Reconnaissance Orbiter. And I joined up with the team in 2006, 2007, and I actually helped develop some of the documentation and became mission operations for the camera for that mission. So that did distract me from my graduate program. But I was able to learn more about the moon, more about moon data, and we actually did start a little bit of a GIS program for that mission. Then in 2012, after I'd been there for about 6 years, I was approached by Dr. Williams to become the data manager for the Ronald Greeley Center. And so that's kind of a convoluted history, but it's all related to GIS, it's all related to planetary. And so now, as the data manager, I'm in charge of the GIS system and helping out students and faculty with their projects in our center.
Well, thank you so much for that. Wow. So it seems to be that you are a jack of all trades. How do you stay current on your skills when you seem to be pulled in so many different directions?
It is a challenge. And the reason for that is there's not a lot of people working in the center right now. So there's the director, and he's focused primarily on his own research. And then I'm the data manager, which means day-to-day operations. We did have a systems manager for our servers, but I've had to take over a lot of those duties. I'm a geologist. I am not a computer guy. So I've had to learn how to do system administration on my own, reading books, learning from others, and so on. We have a web page. It's rpif.asu.edu. I designed that. I had to learn WordPress and develop the content and install all of that. I teach seminars in the center. So I've developed basically introductory curriculum, just a couple hours seminars, what GIS is about, how it applies specifically to planetary, and then also doing the hands-on type of workshops. So all of those are what I work on regularly. And so as you can imagine, I cannot devote my full attention to one thing or another. So there's just a lot of, what's the immediate thing? What do I need to develop a seminar? Do I need to maintain a computer? It's just, it's never ending. So as far as specifically ArcGIS, as you guys know, Arc is always developing. When you go from 9 to 10 or even 10 to 0.1, 10.2, you have to almost relearn the software because they change the buttons, the functionality, and so on. And then Arc Pro has come along. And I've taken a few seminars in that, but it is pretty radically different, the interface between Arc 10 and Arc Pro. So I've taken the seminars, as I said, and I'm trying to teach myself when I have time, so when the new faculty and new students come along, I can train them as well.
Yeah, I can imagine the shift for each thematic area in GIS is different with every time the software comes up and changes.
It is, and fortunately, the planetary data is staying somewhat similar. So if I can just figure out the new technique on the new operating or the new system, then it's easy to work with.
So within the Ronald Greeley Center, who is your audience, so to speak? Is it just ASU research faculty, staff, students, or are you a public center as well? Like if people in Arizona in the GIS community are interested in, like reaching out and finding out what you do, like who's able to access your center and those resources?
Well, we are a NASA facility. We are actually funded by NASA. That's kind of in transition right now, so we're not really sure who our next paycheck is coming from, so to speak. But we were formed and founded by NASA, which means it's taxpayers, which means it's a public facility. So we do have operating hours, so there's times when the facility is closed. But theoretically, anybody who's interested can come in. Data cannot leave the center, so it's not like a library where you can check things out, but anybody can come in and with our assistance can look through books, look through the maps, the old photographs and things like that. Anybody can come and do that. One way to facilitate that is we have a developing online database that you can search through our webpage. And so if you're looking for a particular book or you want to see what's available in our stacks for the moon, you can go through that interface. And so you can look that up at home, come into the center and see if you can find the book, or we can help you find it, and you can review it. As far as GIS is concerned, it's essentially the same thing. We are not turning anybody away, but the focus primarily has been amongst students and faculty. So it's probably about 80-20 with students versus faculty. I have trained is probably overstating it, but refreshing a lot of the faculty about how to use ARC and how it can be applied either in the field or with Planetary. A lot of students come in, they're brand new, they've heard the term GIS, but they don't know anything about it. We do have some students that come in that are significantly familiar with ARC and they just want help with the problem. And you asked about how I learn things or how I keep up my skills. That's a fundamental way on how I keep up. Somebody will bring a problem to me and I might not know how to do it right away. We can call ourselves experts in ARC, but the project, the software is so huge and all the extensives, there's so many different ways to do things. I'm learning things all the time. And so oftentimes a student or faculty will say, we need to have this done. We would like to do this project. And so I'll almost conduct an interview with them and say, well, what are the final products? What are you trying to deliver? What are you trying to solve? And then after that, I'll actually think about that for a little bit, write up how I think we'd do it, get with the person again and say, this is the approach we're going to do this, and then sort of lead them through the process. I don't do the work, but I have to be able to instruct them on how to do the process.
That to me is one of the classics of the best way to learn is through teaching it.
Yep, definitely.
You and I both know quite well is like, we might not know everything, but if you have to figure out how to explain it to somebody, you're going to learn in the process.
Yeah, and there are so many tools. I mean, you go into our toolbox and there's hundreds in there. Nobody can know all of those. But somebody will say, well, I want to look at the orientations of wind streaks on Mars. What direction are they pointing? And I said, well, that's just a compass heading, but there's got to be a way to automate that. So I'll look that up and here's a tool, and just you process it this way, and there you go. But it does take research.
So I'm wondering, how does planetary GIS differ from Earth-based GIS? Does it?
Actually, pretty significantly. I just did a seminar recently where the idea was, how did Earth geology differ from planetary geology? And so back in the 1800s, when geology was essentially a new science, when it was developing, you had people on the ground. They had the rock hammers, they were picking up rocks, they were looking at mountains. It was what they could see visually from their point of view. Then you had balloons that you could take pictures from and do observations at a distance, then aircraft, and then satellites. So our knowledge of the Earth was really from the ground up, okay? Now we have satellites, we have high resolution, planet data is being accumulated on a daily basis. And so Earth has become a planet in the last couple of decades as far as that approach. Planetary geology is exactly the opposite. Mars used to be a red dot out in space. We had to send spacecraft to actually see the surface. And originally the planetary missions were crude. They only took a handful of pictures, low resolution. And so with the succession of missions, we have better and better data. But we're still looking from the top down, right? So our spatial resolution from satellites is getting better and better and better, approaching what we could see on the Earth. And then in addition to that, we also have rovers on the surface of Mars. But if you think about it, as great as they are still kind of a point source. And it's what they can see in front of them or to the horizon. And they are starting to go farther and farther, so we're able to collect more data in the field, as it were. So my point being is that with planetary data, we're starting from the planet and working our way down. And so there are, if you've worked with global data sets before, you have to think about the curvature of the body that you're working with, right? And so one area calculation might be different at the poles compared to the equator. So you want to make sure that you have the right shape when you're doing your calculations and your measurements.
I'm curious on when you mentioned the rover data, I hadn't thought about it in terms of a GIS problem, but your comment that you're dealing with point data and then raster data top down is the primary source of data for Mars. I guess I'm wondering, like, is it possible to interpolate that data, or how does that rover data enhance the larger raster remote sense data sets? Is there a way to interpolate between the two or put them together?
Well, a lot of the rovers make use of stereo imaging. So even though they're looking out, they can make three-dimensional models to make it look like a spacecraft is looking top down. So you can actually look at that spatial data planimetrically, right, from the top down. And then usually that's significantly higher resolution than the satellite data. But spatial data is spatial data. You can register it on a low resolution data set still. And then as the traverse of the rover, as that continues on, they can take sort of these models and plop them down where they collect the data, right? And so now you have a string of data sets that have been sort of arranged planimetrically. So, you can have those high resolution data sets within the larger context of the lower spatial resolution satellite data.
Is it more, rather than discrete point, I guess because the rovers move, sequential? Do they build areas around the rovers?
Exactly right, because the rover camera, it will be on an arm or it's on a staff, and the thing rotates. Okay. And they're like the latest rovers actually have a stereo with two imagers on top of the mast, and so it can turn 360 and collect lots of data. And because it's stereo, the data point of view overlaps, and that's how you can develop a three-dimensional model. So what it really comes down to is how much data does the rover collect at any given site, right? And so the more data you take, the better your model is for the given area. And then the rover will take off, maybe take a few pictures on the way, and then they'll establish a new sort of station, place that they're going to stay a while, develop a model there. And so that's how they kind of build up the data for a given site.
So I just wanted to go back a little bit, because I know that you mentioned some of your projects that you've done in the past, but I was curious, of those projects, maybe could you talk about a favorite project and maybe one that was most difficult in terms of GIS analysis? I know it's kind of a loaded question.
Yeah, I know. The problem that I'll try to answer that question, but the main idea here is that there are missions that go to Mars or wherever, and there is a science team that's associated with that mission or that instrument. And being that they are the first data collectors, they're the first authors, and so they do their analysis that way. It's when a planet like Ceres or Vesta asteroids or Mars, it's when the data sets get built up that really regional and global mapping take place. And so that's kind of further down the way. When you get to a planet for the first time, that data have to be collected before mapping can really occur. And so my interest is geomorphology, so the shapes of things, mountains, hills, valleys, all that sort of thing. And so my master's project, for example, Pathfinder was a lander on Mars back in the mid-90s, and it landed in an outflow basin. So this was kind of where the confluence of big outflow channels dumped material, and then the Pathfinder was going to sort of look at these sediments from that area, and it's what they called a grab bag site. So rather than going to one place and looking at the rocks in situ, here was a place where the sediments were carried downstream, so to speak, and all deposited in one place, so you've got a bunch of materials to look at from a variety of places. So my thesis actually looked at deconvolving the sequence of events for those outflow channels. So this outflow channel came down, deposited, then this one activated and deposited, and so on. Now with Mars, it's kind of tricky to say when it happened. Was it a week apart or was it a million years apart? That's kind of tricky. But you can say this one happened, this one happened, this one happened. And so that was challenging. And, so there was detective work. Back in the 90s, I only had mid-resolution data from the Viking era, so the 70s and 80s mission. And now there's, multiple active missions with high-res data that could be done. I'd actually like to revisit that project with high-resolution data and, see what I got right and see what I got wrong, and sort of create a new map from that area. So I guess, it's a thesis, but I think that was one of my favorite projects. From that time, I've been peripherally involved with a lot of things. So like I mentioned, I help a lot of other people with projects. So I haven't really been involved with something that's just exclusively mine, but I've had the opportunity to work on a lot of things, individually. So that's been kind of fun.
Or maybe you could help us to understand when we think of GIS, planetary GIS, and you started to get at it, like that the mapping comes later after the data collection. That makes sense to, when we think of GIS projects, data collection comes first.
Right.
What are some of the big roles that GIS in general plays in planetary kind of research? Like mapping and modeling would be one, but does GIS play a role in the operations of those missions themselves, on like helping get the instruments to the planet or daily transactions with that mission? Or what are the different roles that GIS plays more broadly in a planetary GIS science and mission?
Sure. Well, the best example I can think of is when I was working for the Lunar Reconnaissance Orbiter camera team, we did our camera image acquisition by GIS. Phil Christensen at ASU and his group has developed a GIS called JMARS. The J is for Java, so it's a Java-based program. And it would actually bring up an image of the moon, a big global mosaic, and it would show the path of the orbiter, where it's going to actually go over the surface of the moon during a given orbit in time. And what we would do is it allowed us to place the footprint of where an image would go. And we could literally drag it up and down that orbit and place it where we thought it would best fit. And so that way we knew things like where the Apollo sites landed. We knew where there were some volcanic vents and some rills. And so we would actually target those images based on that map in order to do our planning. And it made it hugely easy. I mean, so we could do days, because we orbited 12 times a day. And so that's a lot of images per day that we had to stay on top of. And the GIS really facilitated our planning. And so we could do days and days, dozens of image identification very quickly and very easily that way.
So I was curious, how do you do GIS on a gaseous planet? Can you do GIS on a gaseous planet? How would that work?
Sure. The basic idea is if it's spatial and if it has a surface, you can map anything, right? So that's the short answer. I mean, you could map cancer cells if you wanted to. You could take a thin section of that, you can map that. The problem with a place like Jupiter or Saturn is if you take images of it, it's a snapshot. Jupiter rotates once every, I think it's 10 hours, and the clouds are constantly moving. So theoretically, yes, you can map it, but your data is already out of date just a couple rotations later. So the answer is yes, but it's not practical, right? But on the other hand, anything that has a solid surface, even if it does change over time, can be mapped. There is a moon of Jupiter called Io. It is far more geologically active than the Earth is. And so the challenge for that satellite has been, it's constantly erupting, and it's putting new surface materials on the surface of Io. So a map from decades ago will actually have to be updated because of the number of new outflows, the new plumes, the sediment deposited from those volcanoes. And so that's problematic. It's not as problematic as Jupiter, but it is something to be aware of that if you make a mission to Io, if such a thing was possible, you'd have to make sure that your data and your maps were up to date.
You mentioned earlier too on that with each planet you have unique shape, size, models. You know, there's different aspects of GIS you have to be aware of. And I guess I started thinking of like, is there standardized like ellipsoids and datums for each of these planets that, you know, planetary GIS folks use? Do you have reference coordinate systems to reference your topographic maps for Mars? Or, you know, how do you keep it together as the person in charge of all this data in a sense?
Well, the main idea behind that is the shape models are only as good as we understand them. And so Moon and Mars have had the most missions, and so we understand the shape the most. And even then, it really only comes down to two radii, the X and the Y. And so Moon and Mars, just like Earth, is a little bit flattened at the poles. So there's a little bit of difference there. But once you leave those planets, our understanding of the shapes of most of those other features is pretty limited. So we have to go with the default of a sphere with a single radius. And so we're able to get the handle of, you know, just its general shape for the most part. But you know, we just have to go with that, and just, you know, with the caveat that there's going to be errors. You know, and just to give you an example, our understanding of the moon, which is the closest object, was pretty poor until the Lunar Reconnaissance Orbiter got there, you know, just a decade ago. If you were to try to do GIS on the far side of the moon, your accuracy would be plus or minus 10 kilometers, right? You know, so it does make a big difference. A lot of the missions in the outer solar system, you know, originally Voyager just flew by, and so we had incomplete models. And then when Galileo got there in the end of the 90s and early 2000s, it made orbits around the Jupiter system. So it never orbited Europa or Io respectively. During its flybys, its multiple flybys, we built up a model of its shape. Okay, so that's still very imperfect. Same thing for Cassini when it got to Saturn. You know, we have better models of those, but they're still incomplete, still, you know, they're not total data sets of those individual satellites. And so as a result, our models are not that great, but we have a fair idea of what the radius is, and we can map the sphere as such. So that's kind of what we have to work with at this point. There have been talks about orbiting individual satellites. There's going to be the Europa Clipper. I want to say that launches in 25, and that'll go to Jupiter and orbit the Jupiter system. And then I believe there's supposed to be an orbit around Europa. Don't quote me on that. I don't remember. But so we will get better investigations of that system in the coming years.
Is there a reference system like UTM for Mars? Does NASA have a standard reference system for a planet?
The answer is it's the datum that's the problem, right? So like I was talking about, But once you have a datum, you just establish it. You can apply any mathematical model to that. So there is a Mars Mercator, there is a Mars UTM, and so on. And so that's just really a matter of crunching numbers, and you can pretty much develop it the same way as that. So a lot of people will use simple cylindrical for global mapping, or stereographic at the pole. But if there's more of a smaller area that there's going to be focused on, they will do a projection where measurements make sense, like in a UTM system.
So, David, I remember back when we were both at ASU together, I thought there was a big effort with one of the Mars missions in terms of the landing of a device, and the GIS was playing a role in helping with landing of these missions. Were you involved with any of that stuff, or is GIS help to do the navigation for devices as well, with the planetary missions?
Okay, so we're probably talking mid 2000s, right, Chris? Mm-hmm. Right. So there was the MER missions. That was the Mars excursion rovers. There was 2 of them that went to Mars, and they were fairly robust rovers. They actually used the entry system of the bouncing ball. So as the mission, the spacecraft came towards Mars, it would aerobrake with a shield to slow its speed. In a succession of events, the shield would go away, a parachute would deploy, and then balls would inflate around this, and then it was released from the parachute and bounced its way to a stop. In order to make that work, there were several things that had to be met for safety's sake. So first of all, there had to be enough atmosphere for aerobraking. So we couldn't land on a high altitude object like a volcano or mountain because there's just simply not enough atmosphere. So we had to land in a low place. Now we also had these inflatable balls. We don't want to land on sharp rocks, so we had to land on something very smooth. And then we wanted to land somewhere geologically interesting. So how do we couple all of those things so it'll be safe to land, but we're close to something that's interesting, but not something we actually land on top of, so something we can drive to. So there was these types of things that we had to consider in order to place where the rover would go. And because there is some degree of inaccuracy, we can send anything to Mars, but where pinpointing exactly where it's going to land is a bit of a problem. So the landing ellipse, which is a shape that we can put on the surface saying it has a 99% probability of landing within this shape, we can move that to where it's actually going to fit those parameters: a low place, a smooth place, an interesting place. And then once you've eliminated everything else, then you choose which of those sites would actually look interesting.
So it sounds similar to a site analysis that we might do, say, for an urban or environmental context on the Earth.
Oh, sure. Yeah, so the main difference is that on the Earth, you actually got people on the ground that can navigate what's going on. So for Mars, we had only the data sets that we had in hand, and some of the models. I mean, if you have low resolution images of the surface, how can you tell if it's rough, right? And so there was some modeling that had to go into that to sort of prove or disprove how rough a surface was. And that of course, would be problematic. Just a case in point, this is a little bit of history. When we first landed on the moon back in 1969, our images of the moon were brand new, basically. And so when Apollo 11 was on its way down, using the best maps that they had, they actually saw that they were about to land in a boulder field. So Neil Armstrong actually had to take the stick, move the spacecraft, and land into a safe place. We don't have that option with an automated rover or lander. So we need to make sure that our models are pretty good before we actually even send something there.
So we talked a little bit about how remote sensing data is voluminous. How much vector data is available for planets in the center?
So the image data is collected automatically by the rovers and the orbiters. And so just to give you an example, the Lunar Reconnaissance Orbiter, because I know this one, it collected several petabytes of data. That's a lot of data. But even so, when you have all that image data, it still has to be mapped by a person. That's not easily automated. And so the amount of vector data is really dependent on the number of researchers that are actually doing that, oftentimes involving students, and those get developed over time. And so somebody has to write a proposal, they start the mapping process, they edit it, there's a review process before it's published. And that can take years to sometimes up to a decade. And so there is, through the USGS, there are quite a bit of vector-based maps that are available, but not as much as you think. I mean, there's dozens to maybe hundreds, but a lot of them are old. So they've actually taken some of the old maps that were made in the 70s and 80s and redigitized them to be available as vector maps. But as far as new ones, I know of a Europa map that's been being worked on for literally a decade, and that's getting published now. Dr. Williams published an IO map, and there's one global map of that, and I think there's a couple regional maps. So it's a process. Collecting data is easy. Mapping the data, that takes time.
So, what is your favorite planet and why?
Okay.
Is that a hard question?
That's kind of like asking what's your favorite movie or what's your favorite rock band. And
I know. Maybe what are your favorite few?
Sure. Because you mentioned the gas giants. Those are pretty to look at, but they're tough to map. I would have to say that Mars is probably one of my favorite because it has among the most diverse features on the surface. You got mountains and volcanoes, you got outflow channels, there's this highland, lowland thing, big cratered areas, and then smooth areas, polar caps, so it's interesting. I also like the moon, and that's because it's right there. My opinion has always been if we're going to go colonize somewhere, we should do that first, and that means we really need to understand the moon. And then after that, I mentioned Io. Io is fascinating just because of how active it is. With volcanoes literally erupting, probably even daily, it's just fascinating to me how active it is, how the surface changes. We'll probably never set foot there, at least not in several lifetimes. It's just such a hazardous environment, but it's really cool to study.
So similar to, the progression of GIS science, I'm thinking of how issues around time, multimedia, or scale, some factors in GIS that prove to be challenges moving forward. Can you, when we're thinking of applying GIS to planetary geology, is there some unique things that just change how you think spatially or how you want to apply GIS because the data is so different than Earth-based data? I guess it's different and it's not, but have you seen anything that is presents a challenge for GIS out there in the universe that might be different than looking inward at our own planet?
Well, there's a number of ways I can answer that. One, just the data itself is challenging. It's all orbital data, except for the rovers, but it's primarily orbital data. And how do you map a surface when you don't have a good model for that surface? How do you tie down the data so that it's spatially correct? Now that's a challenge, a basic geodesy. And so for Mars, there's a little tiny crater called AIRY-O, AIRY-O, and that is that's the central longitude for Mars. So they had to pick a place. Where do we start? The poles are easy. We put plus or minus 90, but where do you put your central meridian? So I honestly don't know how they picked that place, but that was their starting point. And so from there you go 0. This is one thing that's different with planets. They don't do minus 180 to plus 180. They do 0 to 360. ARC really doesn't like that, and they've actually had to work with the company in order to get that to recognize the data. What's more, some planets go 0 to 360 west direction. So it's actually kind of going backwards. So how do you make your measurements? How do you spatially put your data down when ARC wants to go minus 180 to plus 180 with positive east, right? So I've kind of come up with some interesting problems when I brought in a global cylindrical projection and it only showed me half, because it ignored the plus 180 to 360 range. And so, and it's not consistent. Sometimes I have no problems, and sometimes it won't show me the data, and I'll have to come up with convoluted ways to show it so I can work with that. So that's a challenge. And let's see what else.
Can I just cut in really quickly?
Sure.
I'm super curious on why that is.
What do you mean?
Why that? Did you say 360 west?
For Mars and some other places.
Yeah.
I honestly don't know. I really don't, because originally Mars was 0 to 360 positive east, and the idea is that your central meridian, is 0, and then as you go positive, that's the sun position in the sky. So if let's say the sun is directly overhead on the prime meridian 0, the degrees forward is going to be the day forward, right? It's going to be afternoon and evening and so on. So why they're going backwards, I don't know. But for a place like Venus, Venus actually rotates backwards with respect to the Earth. And so that makes a lot more sense when you want to reverse the 0 to 360 progression there. And some other satellites, they actually have going the opposite direction. And so those are things that have to be, you're aware of, depending on which planet you're working with. And again, ARC just doesn't like 360. And they've actually had to come up with an algorithm. If it's going to be positive west, there's kind of like a switch in ARC that says, okay, we're going to retranslate this value for the opposite value. And that's actually a tool that was developed out of Flagstaff as well. So anyway, these are not problems that you'd find on Earth. And so it does make some things challenging.
So I'm personally fascinated by planetary GIS, and I bet so are many of the people who are currently here listening to the podcast. And if one wanted to learn or get more involved in this area, what would you recommend to them?
Sure. Well, the first thing is take a class in GIS. That's kind of the obvious thing. There are a number of students that try to learn ARC online. And they say, well, it's just like Illustrator. It's just another software package to learn. And on the face of it, it is. But ARC is more than that. I mean, it is spatial data. And if you project something into maybe the wrong planet, or you forget to go from a datum to a projection or something like that, you are going to make what I call spectacular errors. There's one guy that I know, he didn't put his final project into a projection. It was still in the datum. So when he was doing his calculation for area, it came out in square degrees, not in square meters. So the data were meaningless. Fortunately, that was corrected before he defended. But the point being is that you don't necessarily learn things like that directly if you learn something through a YouTube video or from a book. So being in a classroom, working on a project, getting instruction, helping, being helped by others, that's really the best way to learn GIS, even only for just GIS 1, and then you can continue on from there. So definitely take a class or get some sort of seminar instruction. And then the next thing is, if you're interested in planetary missions have gone from big names at institutions to working with students and even the public to some degree at individual sites. So for example, bring back the Lunar Reconnaissance Orbiter again, because I worked with them. They have freshman students with no planetary background at all helping around the office, maybe starting with clerical work, but starting to get involved with the actual active missions. So there was one young lady who came in, brand new student, and she said, I will deliver coffee just because I'm so interested in this. And they said, no, your enthusiasm shows that you want to be here. We will actually train you to become a planetary geologist. She got her bachelor's degree, and now she works at JPL as one of the mission operations there. That was just by her taking the initiative to go meet the person in charge of the camera, say, this is what I'm interested in. I really like what you're doing. And she got what she wanted. That I think a lot of people are not aware of. They see the mission, they see the money, it's NASA. That can be intimidating, and they never actually go give it a try. That's how I did it. Mark Robinson, who's in charge of the camera, actually came to ASU in 2006, And I said, I need to talk to this guy. And I set up an interview, and we talked about things. And by the interview, at the end of that, he said, yeah, go ahead. You can work for me. We're going to do this. And so my main thing here is just take the initiative, find out what it is you want to do, and go for it. But as far as the GIS, it's good to have that educational background to couple with the geology that you're going to be learning for the surfaces of the planets.
Let me ask you one last question about the Ronald Greeley Center for Planetary Studies, David.
Sure.
If the GIS community in Arizona was interested in looking at some of your data sources, is there publicly available data online that they could go look at and try poking around with and making little models of themselves for public use?
Sure. At this point, most of the data that we have on our servers came from the USGS. They provided like the base maps for Mars, for Io, for Venus, and so on. So all of those are publicly available now. They're constantly working on their website to expand the data sets and make it more user-friendly and so on. What we as the center do is we use that data for training purposes. Now, we do provide some vector data. So, for example, I mentioned that Dr. Williams had actually developed the geologic map for Io. Those are on our servers, and people can work with those on site. If you're a student or a faculty and you want to work in our center, I usually right now I have to provide the data to you, or you generate the data yourself based on the map data provided already, the base maps. What I'm trying to work on is we do have lots and lots of data on the server that I would like to be able to serve up. I'm learning how to do that. I've never actually worked with a data server before. And so while we have it in our directories, I want somebody to be able to point to it through a link or connecting to our server. And that's something I have to learn at this point.
Well, thank you for joining us today, David. It has been great to chat with you and to learn more about the work you're doing at the Ronald Greeley Center for Planetary Studies, and to exposing us and the pod people of our tens of listener universe to Planetary GIS. So we're very excited to send them out to explore the universe more and learn more about how GIS is not just an Earth-based phenomenon, but can be applied, to any sort of surface or sphere. Do you see any fun future things that GIS might, help us boldly go into the future in planetary GIS that you're looking out for it on the horizon?
Well, every time we go to a new place, it's new data for us. So there's a small asteroid called Bennu, which is only 500 meters across, and they're currently in orbit about that, mapping that. So as small as an object is, they are mapping that. The next mission that is coming up on the horizon is we are launching, I want to say in 22 and getting there in 26, and this is to Psyche. This is another asteroid in the middle of the asteroid belt. The idea is that it is the remnants of a core of a planet that might have been demolished or incompletely formed. So it's mostly metal. And we are going to be mapping a brand new planet-like object that is totally alien, not a rocky surface. It's not going to look like anything we've seen before. It might look like a ball bearing in space, or it might still have a rind of silicate material on the surface. We won't know until we get there. But that's a new place that's going to be completely new. It's going to be completely photographed. There's a suite of instruments on board that mission, the Psyche mission, and it'll be exciting to see a brand new place that we've never seen anything like it before.
Well, thank you for joining us today, David. And
okay, glad to be here.
Hearing more about the center in the future.
Okay, and thanks for inviting me, and I hope it was informative. And if you have any other questions, you can always email me, and I can add to this at a later date.
Thank you so much.
Okay, you're welcome.